Hello, my name is Jonas Österg Andersen, and today for this lecture from the ENIGMA-U series we're going to talk about spatial memory. Imagine that you're going to navigate through your environment and you want to go to the grocery store. Most likely, you have a specific route that you always follow to get to your closest grocery store. Now, when you go there, suddenly an obstruction in your route appears, making it such that you need to figure out, well, what do I do now? Most likely, you're able to adapt to the situation and then find an alternative route just on instinct and thinking around it, and then follow it to get to the grocery store. Now, what this really shows us is that spatial memory is not just restricted to navigating through a single specific route. However, it is also practical when it comes to situations where changes into the environment occur, making it such that our memory support behavioral flexibility, making it possible to adapt to changes in the world around us. Now, spatial memory is defined as our capacity to remember the position and location of objects or places, which may include orientation, direction, and distance. Spatial memory is essential for learning new routes in addition to supporting navigation. Now, when having studied this in science, we have discovered that one particular part of the brain has been very much related to navigation, which is the hippocampus. So this was pioneered by Brenda Milner when we were studying a patient named HM. He suffered from violent epileptic seizures and had to have 2/3 of his medial temporal lobes removed, including both of his hippocampi. What they discovered when he woke up after his surgery is that he was no longer able to recognize the hospital staff, nor find his way to the bathroom. He was also unable to recall anything from the day-to-day events of his hospital life. So patient HM suffered from something we called anterograde amnesia, which is the inability to form new memories. And considering how the hippocampus was removed after the surgery, we narrowed it down to realizing that the hippocampus is necessary for forming new memories in both humans and also in rodents. The hippocampus also seems to be particularly tuned to spatial representation, and this in particular has been studied in rats through using an experiment called the Morris water maze. The Morris water maze works as such that you have an arena that is filled with opaque water. You have inside this arena a safe platform that is not possible for the animal to see, and then you place the animal into the arena. So when this happens, the animal will try to explore its novel environment and then at the end be able to locate the hidden platform. When testing the day after for learning, then you will see that the animal, once placed back into the arena, will move directly to that safe platform. Additionally, if you place the animal in a different location, then it will also be able to navigate to the correct platform, indicating that the animal has a stronger or more objective representation of its environment. So, how do we then test whether the hippocampus is necessary for spatial learning? Well, we perform a lesion into the hippocampus, which is a localized damage to any particular brain structure. So, basically, you just destroy the hippocampus and see what happens. Now, if we were to perform this procedure, what would happen when we place the rat back into the water maze? Well, if we assume that the hippocampus is necessary for encoding spatial memories, then what we would expect to find is that the hippocampal lesion would inhibit the rat's ability to learn the position of the safe platform. Now, we can then perform this experiment with both a lesioned animal and a non-lesioned animal, and both will then, during the first exposure to the arena, try to locate the platform, explore its entire environment. The day after, the animal with the intact hippocampus will be able to locate the platform right away, while the animal with the lesioned hippocampus will spend longer time trying to figure out where was the safe platform as if it was completely new. So this is all consistent with the cognitive map theory that was postulated by Edward Tolman in the 1940s. Now, what he was thinking, after seeing or performing a lot of animal experiments in different types of mazes, he thought that what is happening is that animals are able to create a mental representation of our environment and its attributes. So to summarize what we've learned until now, we see that damages to the hippocampus in humans causes anterograde amnesia. We see that the hippocampus has been shown to be necessary to support spatial memory, but then one question remains. How or what is the neural mechanism that allows the hippocampus to represent space? And this was answered through the discovery of hippocampal place cells. Now, place cells are basically neurons that exhibit preferential firing at specific locations in the environment. So this was discovered through implanting electrodes into the hippocampus to record the electrical activity of the neurons and then put the animal in an open arena. And what they discovered is that these place cells seem to specifically fire action potentials at a specific location in the environment. And the discovery of these hippocampal place cells reveal a neural circuit of navigation and spatial memory. So here's a video of a rat that is being placed into a square arena. And as you can hear, the animal or the cells in the hippocampus will fire action potentials at the or whenever the animal is in the upper right corner of the arena. So when then studying these hippocampal place cells, when we can discover different firing fields of these neurons. What is happening here is that when we try to measure several hippocampal place cells, we discover several firing fields that in sum will cover the entirety of the arena, making it such that the hippocampus has a mechanism that it can track the position of the animal wherever it is located in space, giving us basically the cognitive map that Tolman was talking about. Now, this has also been studied in humans using functional imaging. So, a small note here. I did misspeak a bit because I didn't mean to say functional imaging, I meant to say structural imaging. So they try to study the differences in the size of the hippocampus between taxi drivers and the normal population. However, many different scientists have applied different types of methodology, so spatial memory has been studied through using functional imaging and structural imaging in the past. So just a bit of a clarification there. I hope you enjoy the rest of the lecture. Thank you very much. So a very famous example is through studying taxi drivers who are working in London. So London taxi drivers have to learn approximately 320 routes, 60,000 streets or roads, and 100,000 places. And when comparing the volume of the hippocampus between the taxi drivers and the regular population, we see that the hippocampus of the taxi drivers is much larger than the regular population. And this is of importance because we have discovered previously that the hippocampus is related to spatial learning. So we also can see this in more subtle ways. For example, through memorization techniques. Now, one of the most effective ones is the method of Loki, where you basically make a memory palace. You imagine a place that you've been to before, and such as maybe a previous place that you've lived, and then you make a route in that environment. After that, you have a list of elements that you place at the different areas of your route, and during recall, you try to navigate through that same route to remember the list. So to summarize what we've learned so far, Spatial memory is necessary for navigating through the environment in our daily lives, and the neural circuitry in the hippocampus seems to be the one that underlies our ability to form and retrieve spatial memories. Now, it's important to keep in mind that spatial memory seems to go beyond the hippocampus and likely involves the entirety of the brain. So, as you can see here, marked, or the areas that seem to be colored here, is basically the areas that are active during different navigational tasks. And here you can see that the activity is not just restricted to the hippocampal formation, but it is also very much distributed throughout the entirety of the brain, showing us that spatial learning and navigation requires a much more distributed network of activity. It is not just restricted to a single structure. If you are interested in reading further into the topic of spatial memory and navigation, here are some of the resources that explores place cells and grid cells which together participate in our representation of space. Additionally, here is also an article that discovered place cells in humans, and also an article that discusses how the entire brain is involved in navigational processes. Lastly, I would like to thank my coworkers who contributed to this presentation. I hope you enjoyed this lecture regarding spatial memory and that you learned something new. Thank you very much. Here are the references.